We got a box held stationary. Again, here's the key. No net force, which means all the forces in the horizontal direction and the vertical direction must cancel. Meaning if there are forces to the right, there has to be forces to the left. If there are up forces, there are down forces. And it's one of those things that once you know this box is in equilibrium, it's not accelerating, there's no net force. So this is me setting the horizontal forces equal to 0 because I know it's not accelerating, so I know the right force minus the left force has to equal 0. So T2 is pulling it straight to the right, T1 is pulling it left. How much left? T1 cosine theta. And in this case, I believe I actually know that T1 is 100 and the angle is 30, and so I can actually figure out what T2 must be exactly. Okay, on this side, I know that this is me saying, well, the box isn't accelerating up, which means the net force on it, up versus down, have to be the same. So look at T1. T1 is pulling up on it. The weight of the box is down. So that must mean that T1 sine theta, the vertical component of T1, must equal the vertical component of gravity. Now, there's no component of gravity because all of gravity is down, which just means that T1 sine theta minus mg has to equal 0. Plug in those values, and I get how much the box must weigh. Okay, so I found values for all of those things. Again, over here, I found what T2 was, and over here, I found what the gravitational pull, meaning the weight of the box is. But it's all about if I know that the box is held stationary, there's no net force. That means that the two ropes in gravity are all working together to balance. And that's what this is saying, horizontal balanced, vertical balance. Okay. This one, I just want to find the length of that diagonal. And so hopefully in class we actually discussed the three-dimensional Pythagorean theorem. If you look at this, I picked nice numbers. If we just wanted to go across the little d, the diagonal of the base, it'd be 8 over and 6 up. So if we wanted to figure that distance out, it'd be 10. But then if you think about that diagonal 10 and that 24 up, that actually is a right angle right there. That's a right angle. The base diagonal, the height, and the big diagonal of the rectangular prism actually do form another right angle. And so where did this 10 squared come from? Well, that's really just 8 squared plus 6 squared square rooted squared, and you end up with this. You end up that the distance in 3D is really just like a delta x squared plus delta y squared plus delta h squared. If you tell me you understand the two-dimensional Pythagorean theorem of going across, right? Delta x squared plus delta y squared equals the diagonal squared, then you also have to agree that the three-dimensional Pythagorean theorem is in fact true. And you end up saying that the distance from the front bottom left to the back top right is 26 centimeters based on that box. All right, so this one is just talking about how far these people are away. Okay, person A is 30 east and 40 south. So I kind of drew this right and down, again, right and south. B, and he's on the ground. Person A is on the ground. Person B is west and north, so left and up. And so the question is, how far are these people away, considering B is in a hot air balloon? Well, just think about their x's. One is 30 right, and the other is 45 left. Well, the difference between those would be 30 minus 45, which would really be 30 plus 45, and they're 75 meters away. Vertically, same thing. It's like a 60 minus a minus 40. Or a negative 40 minus a 60. Doesn't matter. Either way, you're going to get a net of 100. They are 100 vertically away, 75 horizontally away, and then 50 height-wise because A is on the ground and B is in the air. So really, you have all three dimensions. The distance in 3 dimensions is going to be delta, I switched these, delta x squared plus delta y squared plus delta h squared, and then square rooted, of course. Okay? All right, this one. This is how much did the helicopter ride increase their displacement from each other? Okay. Oh, okay. So person D, we're just adding another dimension here, right? So person D is just going to end up going up and going in that third dimension. So it tells you person C is 230 meters away at an angle of 30 degrees north of east. North is up of east, which is right. So up of east. That's this right here. That's this blue. That's C. C is 230 away from the origin at an angle of 60. D is 400 away at an angle of 55 degrees west of north. So west of north, meaning left of up. And so you can see I didn't actually label 55. I went ahead and labeled 35 because that's the angle I want. That's the angle that was given. That's the stupid angle up top, is that 55. So I went ahead and labeled 35. And then I'm going to break these pieces down. Where is C located? C is located at that x value. Now, where is D located? Now remember, D is left. So the difference between where C is and D is, well, I'm actually adding those pieces. Again, you want to subtract because it's the difference. I get it. Delta. Delta means the difference. That's okay. You could have just said, in reality, a little more formal. You could have said this minus this. The difference between their positions. And what you would have done was, this would have been a positive. You would have subtracted a negative. I just went ahead and added them together because I know C is to the right and D is to the left. So the total delta between them is just adding their two positives together. And then y, so of course I did subtract because this is how much D is up and this is how much C is up. And I subtracted, and I only did D minus C because I knew D was, well, I guess I anticipated D just being a little bit taller. Okay, again, why did I subtract the y values? I really subtracted the x values too. I just subtracted subtracted a negative and put a positive. Either way, I now know this is how far they are horizontally away. This is how far they're vertically away. This is how far now the helicopter up they're away. So then the total distance is the 3D Pythagorean theorem of the two people. All right, this is your classic wind and plane. So I got a plane traveling at 40 meters per second at 20 degrees east of north. I didn't label that. I said 70 degrees because east of north is this top angle. East is right of up. So that's this 20, so I labeled that 70 because it's better. And then the wind is 30 meters per second at 55 degrees south of east, which is the correct angle we want, the horizontal angle, right? South down of right. And then the result, remember the resultant, is the combination of what the wind does to the plane, and now we have the actual net result of that. So what I did is I took the plane's horizontal plus the wind's horizontal. I then took the plane's vertical minus the wind's vertical because the wind is down. And then I got those two pieces. That's how fast now I'm flying horizontally. That's how fast I'm flying vertically. I then did the Pythagorean theorem to find out how fast I'm actually moving total. And then I did inverse tangent to find the angle. And then you can figure out, well, did the wind slow it down or speed it up? Well, the original plane was moving 400 meters per second. And now you're only going 400 meters per second. So what did it do? Well, it bent you. The wind bent you down, because now we're only at 66 degrees versus 70 degrees, and it slowed you down a little bit. That won't always be true. You know, wind certainly can speed up the plane, but this wind was enough down that it actually made the resultant vector shorter than the original vector. All right, we got a boat trying to cross a river, okay? If the boat doesn't make an adjustment, it's going to go like this and float down and end up there. If it does make an adjustment and tilt itself, well, then can actually go straight across as long as the boat's vertical speed cancels the vertical speed of the river. So First part says if no corrections are made for the current. So boat is pointing straight across the whole time and you're just going to go, and you're ending up down here. So no adjustments. That just means, well, your horizontal distance is your horizontal velocity times time. So I got to go 450 meters horizontally. I'm traveling at 15 meters per second horizontally. So it's going to take 30 seconds. What's happening vertically? Well, the river is going down at 3 meters per second, but I'm going to drift 3 meters per second for the 30 seconds, and I'm going to drift 90 meters downstream. In this case, the boat's velocity and the current's velocity don't have anything to do with each other. The boat's going horizontal, the river's going vertical. We don't adjust. They actually don't affect each other at all. Now we want to make a correction. So what angle is necessary so the boat actually goes right across the river? Well, what does it mean to go straight across? It must mean that the boat's vertical velocity, when it's tilted up, is exactly equal to the current's velocity going down. So all we need to do is tilt the boat up so that we create a vertical component in the boat of 3. And that's what this is saying. The boat goes 15, and I'm going to use it to tilt it up. And I'm going to tilt it up at an angle such that my vertical component is 3, and so that when I add the component of the current, the 3 and the 3 cancel each other, and I go straight across. So it turns out that if I want to find that angle, I'd use inverse tangent of 3 over 15. And I say, all right, if I point exactly at that angle upstream, I'll end up going straight across. My vertical component will cancel the river's vertical component, and so I won't have a vertical velocity. Well, that just means I will go straight right. All right, this one, kind of the classic, got a bunch of forces acting on this thing, and okay, so the question is, will this object experience a horizontal acceleration or vertical acceleration? Well, I know we don't know Newton's second law, we haven't a ton of examples on it, but if you have a net force in the horizontal direction, you will accelerate to the right. If you have a vertical acceleration upwards, you're going to accelerate upwards. And so I gave you this picture. It's like a box on the ground, and there's all sorts of stuff acting on it. There's an applied force that we are pulling at a certain angle. There's friction opposing it. There's the normal force of the table. There's gravity pulling down. None of those things you actually need to know. You just have to know that this picture and those values are true. And so let's look at it from a horizontal point of view. So FA cosine theta, that right there is the horizontal component of you pulling. And the only other force that's horizontal is friction. So hopefully it makes sense that if the horizontal component of your applied force is bigger than friction, you're going to accelerate to the right. And it turns out that that is 56. So yes, you will accelerate to the right. How fast? Well, it would depend on the mass, but we do know you will go that way. Now, vertically, you have FA sine theta that's up. You have the normal force that's up and no angle because it's straight up. And then you have mg, which is down, which is why I subtracted it. And then if you add and subtract those bad boys, you get 0, which means the 3 vertical pieces all perfectly balanced, so there's no net force in the vertical direction. If there's no net force, there's no acceleration vertically. Okay? All right, this one, it's suspended. Suspended means, dude, it's not moving. Everything is balanced. So that means the horizontal pieces and the vertical pieces must balance out. So what's pulling this thing to the right? Well, T2 is. How much of T2? Well, the horizontal component of T2, that piece right there. That amount of T2 is pulling it to the right. So T2 cosine 30 is pulling it right. T1 is pulling left. And since it's suspended, not accelerating, we know that those have to equal 0. Then we can write a vertical equation. We know it's not moving vertically. So then T2 sine 30. So this piece, that piece of T2, the up part of T2, right? T2 is pulling right and up. The up of T2 has to balance the down of gravity. And at this point, if you look at this, we can solve for T2 because it's the only variable we have in this equation. And we solve for T2 here. And then you can take T2 and plug it into this equation to then solve for T1. And then you actually find both T1 and T2 based on those two equations. Okay, but again, the idea that if it's suspended, we balance the forces. We balance the forces by balancing the pieces. This is right minus left, up minus down. And we're setting them equal to 0 because it does say in the problem, the weight is suspended. This will be the exact same thing. There's some weight, it's suspended, it's not moving. And the only thing you have to be careful of is the fact that these angles are stupid. They're the vertical angles. Now, traditionally, like this 30 degrees, it's the angle with respect to the horizontal. Well, these are the verticals, so we just have to adjust. And you can see the x hat has sines and the y hat has cosines. Well, yeah, if you switch the angles, you're going to switch what sine and cosine are. It's no big deal. So in the x direction, we can agree that T2 sine theta, right, the opposite side of that angle is there. That's how much T2 is pulling right. That guy is how much T1 is pulling left. But like, look, they're pulling left and right the same. They have to be. The angles are the same. So if T2 sine theta must equal T1 sine theta and the angles are the same, then those two ropes have to be the same tension. If they're the same angle, they have to be the same tension. Now, from the y point of view, this is how much T1 is pulling up. That's how much T2 is pulling up. And then that's the weight. And we know it's equal to 0 because it's not accelerating. Now, in this case, we already decided that T1 actually equals T2. So this really just says 2t cosine theta, right? We can add those together and get, we can get 2t cosine theta equals w, and then we can divide. And again, this answer is non-numeric. This is just in the abstract, that we know that the tension in the string must be w divided by 2 cosine theta. All right, this one, we got a block, and we want to decide if it accelerates, and we want to decide what direction. So we just have two forces. So we're going to take Sam's horizontal plus Alex's horizontal and get a horizontal force. So yep, it's definitely accelerating to the right. And then we got Sam's vertical minus Alex's vertical. Alex is pulling down, so we used a minus, and it's down. So Alex is going to beat Sam's vertical. And so yes, this will accelerate to the right and down for sure. All right, this one, this is the picture. And it's moving in a constant velocity. Constant velocity means no acceleration. No acceleration means no force. So there's no force on this thing, which means everything is balanced. That's all I'm going to do. I'm just going to break down the vectors. There's the horizontal vectors. There's the vertical vectors. It's nothing more than the right minus the left equals 0. The ups minus the downs equal to 0. Since those are balanced, all this other stuff is just me doing algebra and solving for things. Again, algebra after physics is really the setup. So getting this set up is physics. The rest of it is just doing some math. What do we got going on here? It's kind of like a longer story, but it's really nothing more than breaking down vectors. So I have F1, F2, and F3, and you want to find F1, right? And so let's read the story again. So we got 3 kids all pulling on this toy. So kid 1, kid 2, kid 3, they all pull with some force that makes the toy stationary. If the toy is stationary, there cannot be a net force. So again, we're just balancing all the forces. So write them out in the abstract. This is kid 1 pulling right. This is kid 3 pulling left. Kid 2 doesn't help left or right, which is why in the horizontal piece, there's just F1 and F3. Now vertically, F2 is straight up, which is why there's no sign. And then F1 and F3 are down, which are why there are negatives. Okay, so we're going to bust up, and it looks like there's all sorts of substitutions and other things you can do, but I think you know everything but F1 and angle 1. So you can figure out what this is, F1 cosine theta 1, and then you can actually figure out what F1 sine theta 1 is. So I didn't actually figure out what F1 and F1 was yet and theta 1 yet, but I found out what their pieces are. So this must mean the only way this can be balanced is if F1 pulls 26.3 to the right and F1 pulls 20.8 up. And so what I did here is I used those and I drew that picture, and then I did Pythagorean theorem to find 33, and I had inverse tangent to find the angle. And so this is a picture that I didn't feel like changing because it's kind of like, I don't know, it's kind of a trick one, but how would you adjust the arrow to reflect what truly kid one has to do? Well, it turns out, look, you just said it. Kid one has to pull to the right and up. So really, F1's arrow should be probably much shorter, and it should be up and to the right. So F1 really should be drawn up there if it's drawn where it should be based on all of these things canceling out. Again, think that through. This is really just a system of equations. I could have solved for F1 and then theta 1, but I actually solved for F1 cosine and F1 sine, and then I had this triangle, and from the triangle then, I used the Pythagorean theorem and inverse tangent to actually find F1 and theta 1. All right, hopefully that helps. I understand that this is a pretty long one. It's definitely more intense, but you should have gotten a decent amount of time in class to kind of work through this.